I also don't want to say this. I have one. Yeah, I do not like research stuff. I don't have I'm not doing a career fair. Tuesday, Wednesday next week. Don't. I don't like it. I guess Wednesday.
She graduated, I wish she wouldn't do that. He takes off like black points, sort of like.
At least one
That's why they're working on
up, down.
What's his name?
Yeah, he's also a single hundred.
Well, he's gonna cover class. I'm pretty sure all the classes.
Yeah, you coded that.
They also
I did like 3 or 4 times, so I'm pretty confident that it's bipolar, not polar. That was her mistake. We gotta alternate your ones. One of them so you just got to check units. Yeah, I think it's because of answer. These cancels can be very hard. Communication systems, workouts, proofs.
Yeah, mine.
I'm sorry, I'm not like what's happened so much which is good.
I gotta try to stick my own.
That was a very elaborate. I'm not gonna correct you. You did that nice. To the power of you only appreciate it now. Say 100 minus. Join that. You like join. I've got
So, before I start, questions about anything related. Did you all watch the video? How many did? That was a very informative video. It went through, showed you what you needed to know, and at the end of the day, I don't know if you caught this, but there's really one thing you need to know when you're talking about slap waveguides. Well, two. Are there any questions about anything related? Because I'm just going to tell you the bottom line of this. With a slab wave, this is a brand new marker, by the way. They use the index of refraction typically, and they'll talk about some N1 and then N2 surrounding. And again, N in general is the square root of epsilon relative for the median. It's just the index of refraction. Are you with me on this class? Now, there's two basic things when you deal with slab waveguides you need to know. One is, because that field never goes to zero at these edges, it just kind of, basically you get an evanescent field into the actual layers, the surrounding layers, and that evanescent field, the energy in it comes back. Because that happens, you actually never get, you have a mode called the O mode. It's basically a mode where you can propagate electromagnetic energy in this thing down to almost DC. Now, you're going to have to just accept that. It's true. It will bounce around. There'll be a lot of things that happen as far as how the field's dispersed in these media surrounding it. But ultimately, it'll just bang around there if it's at the critical angle or higher. Now, the one thing that's important is when you have a slab waveguide, and this is the dimension here, A, that for only one mode only, it requires this, and this is in Dr. Wentworth's book too. A, that dimension over lambda naught, and lambda naught is going to be the free space wavelength, so that's C over F. Remember that. It has to be less than 1/2 over the square root of N1, that's the sandwich of the actual height value, minus N2 squared. This is the criteria for a single mode. Y'all follow me on that? Now, any frequency below that will only propagate a single mode. Why is a single mode important anyway? Why don't you want 2 modes or 3 modes? Because, the velocity, then you will have power split in the modes and it'll propagate at a different velocity. Y'all follow me in this class? So, for single mode, after all said and done with those equations, then you get the solutions to the del squared equation here and here, and you match the boundaries with the solution in here, and you get these trajectories. Basically, they're tangent functions. You find the solutions where they intersect. After all that's said and done, just to show you the modal values, they come out at the end of this and say, if you only want one mode, which you do, you have to meet this criteria. And if you meet that criteria, you check the boxes. That's it. Now, there's a lot more to this, but it's much more advanced, and we can't get into it. But that's really it. Do you follow me on this class? And there's something else I got to tell you. Now, in that video, he didn't go through this, but see, this is called a step index, actual type of slab waveguide or dielectric guide. There are graded indexes where you'll have N1, but instead of going just abruptly from N1 to N2, it will gradually go to N2, and you'll have something like this as far as the profile. If this is the value of N, it'll look like this, and then it'll come down to a lower value. This would be like N1, and this would be N2. This is called a graded index, and they do have those. There's reasons for that. Basically, a graded index fiber, a graded index slab waveguide, for all intents and purposes, is a lot easier to build when you're dealing with real small dimensions, like submicron to typically micron or less dimensions. They're easier to build this. harder to build that thing like that. So anyway, that's it, really, for a slab waveguide. How many knew that was the actual one mode condition? Does anybody remember that? One? You did? I put it on one note. I want to make sure that's the one thing you remember about a slab waveguide. Now, when we talk about fiber optic waveguides, and these are optical wave, well, the fiber optic. Now, we're talking about cylinders. And basically you have, instead of a sandwich, you have something, and it's called a fiber, right here. It's just a straight, constant cross-section, and it's the fiber, and it has actually a radius of A, but normally this dimension, the diameter is 2A. And it's surrounded by something called a cladding. Then, around there, that's not drawn right, but around there, there's going to be cladding. And that cladding is just like the sandwich over there in terms of the values of N1 and N2. Let me just draw this up here. So you're going to have this, and it'll have a radius of A, and then you'll have something called a cladding, NC here. Now, NF will always be greater than NC, or this thing won't work. This is what they are. The dimension of that is A, and typically they give you the outer dimension of the cladding here. And here's the way this usually works. So here you have 2A, and this is really going to be the diameter of the cladding. So when they designate fiber optic cabling, it's typically done this way. You'll see something like 50, 125 fiber. It'll be a designation. The 50 is actually the diameter of that. This is really equal to 2A, and this is 50 micrometers. They don't put it on here. This is microns. They don't ever show this, but it's 50 microns would be 2A, and the 125 would be this diameter. Would be the diameter of cladding. Now there's one other thing I'm just going to show you physically what they are. Get a good picture of that in your mind. You just have, basically, you've taken this sandwich and you've made it into a cylinder, basically. You've got an inner core, it's got a cladding value that's hot, and it's glass, and then it's surrounded by, it's really a fiber core, and then you've got cladding around it. And the wave just ricochets down that just like it does there. But I'll tell you this, he doesn't say it in his book. The lowest order mode there will be the 1-1. It'll be a TM11 mode. We're not going to prove that because it takes a solution of Bessel functions, and I've asked people about this, and they don't feel it's appropriate for this class. You'll get this if you do anything at the senior level with optical fiber, anything like that, you'll see this. They'll go through the whole analysis. I still may do that. I'm still threatening to do it if I have more time here. But when they designate stuff, they don't bother putting microns here. It's assumed microns. So it'll be 50, 125, or 25, 100. And they're the dimensions of the inner core and the outer core, the diameters really. Follow me on that? That's the way they're designated. Has anybody worked with fiber optics around here? You have, is it glass fiber or silicon dioxide?
Yeah, it was silicon dioxide for camera systems.
For camera?
Camera systems, yeah. We ran fiber backbones.
I'm going to put up a video. It's really good. It shows actually a fiber optic tube. When you go beyond a certain critical bend, all of a sudden it doesn't work. Then you get terrible reflections. Fiber tubes and stuff like this, they have a maximum, they have a what's called a minimal radius of curvature that you can actually bend these fibers at before they start really spraying signal all over the place, and you don't get any transmission. But what's amazing is Dow Corning and DuPont are some of the manufacturers, and they've taken silicon dioxide. Now that's quartz. When I think of quartz, I think of something that's not pliable. It doesn't bend well. But they've added materials, these are material scientists, so that they can get these thin fibers that can be bent. And it's amazing. Has anybody seen this stuff laid in the ground ever? They did this in front of my house not too long ago. Spectrum had eminent domain, and they dug up my front. And I watched them lay the cable in there. And I thought it was gonna be real big, like some of the fiber communication systems I've seen in the past. It was about that big, it was much smaller, and I don't, does anybody realize this, the size of the cord, of the diameters of these things that come way down? Have you ever seen fiber laid? All right, first time I saw it was years ago, and the cabling was this big, and they're putting it in. It was off these giant spools, and they had to be real careful they didn't bend it much. Nowadays, it was really, I was surprised, I was shocked how small it was. So anyway, yeah.
You said the lowest order mode that it operates in is 1-1.
Right. And I'm gonna tell you one thing, the only way I can prove that to you, if you really want me to, I will. Come see me after class, and I'll go through the derivation of the del squared equation for this, for a cylindrical waveguide, will match boundary conditions, and I'll show you. It's an interesting thing, but it takes, honestly, it takes about a good hour to do this. It takes a while. If you think the del squared stuff with the rectangular guys, it took a little time, that's nothing compared to this. It takes some time. All right, so with this thing, we're gonna go ahead and analyze it. That's basically fiber optic cable, and there's one other thing too. Outside of here, there's always something they call the jacket. Now Dr. Whitman's book has a great drawing of this. If you can look online, I'll tell you where this is though in the book, so you know. This is page 407 is where he does the drawing that I'm showing you. And the jacket is around there. The only thing the jacket does has no electrical, it has no impact on the electrical behavior or the photonic behavior. It keeps the thing from getting eaten up by rats and stuff. Now, I don't know if you know this, but when you cables, anything made with an oily residue and stuff like this around it, rats and stuff like this love to chew on it. I had my boat, all the wiring in my boat chewed, really just, it was chewed up by a bunch of rats or field mice. And I didn't know that, but cables that have any kind of, are made of any kind of oil product, they just attract critters and they love to chew on it for some reason. So that jacket is made especially to deter anything like I guess a groundhog or a rat or anything from chewing through. That's the only thing it does. You don't have to worry about that ever. If it's damaged, don't worry about it. This outer jacket. Now, I wish I had a piece of this to show you. I don't right now, but I'm going to try to get one. Can you send me an email something? I appreciate this when you remind me. I will get, and I'll show you a piece because it's going to be. If you think the waveguides are boring, Sam, this is even. It looks like a straw. That's all it looks like. Now we're going to go through the analysis of this. And we're just going to do a wave. A bounce diagram on this thing. We're not going to go through, I wish I could. I'd like to go through the del squared equation, field equations, the entire development, but this is a little much. So, when we look at this, I'm going to take a look at the cross, really, I'm going to just cut the wire down the middle and look at it longwise. So, here we have the actual core, right here. Dimensions of this thing are 2A, and it's really, they call it the fiber core, has an index of refraction NF. Then you have a light source external, and there's an index of refraction N naught. Now usually if we're talking about air, the index of refraction would be 1. Y'all follow me on that? Because N is just the square root of epsilon relative. Epsilon relative of air is 1. What they then talk about is they're going to have optical light coming in at some angle, and this is theta incident. Then, as it goes through here, it's going to bend, and there'll be a second angle. I'm going to call, he calls this theta A in the book, so I'll call theta A. This is theta B. Now, here is what's interesting. They want total internal reflection. So that means the angle here, you might say this angle is now going to be 90 degrees. This is the analysis. They're assuming the only way you get propagation is if you get the wave totally reflected. So this angle right here is going to, this angle is going to be the critical angle to make sure that that angle is 90 degrees. Do y'all follow me on this class? So when we take a look at this and we analyze it, By the way, I strained my back trying to replace a leaky toilet. And that's before. I don't know if anybody's ever done that. I haven't felt that bad since deadlifts longer. Anyway, when we go through this, do you have a question?
There, is that H naught or A naught?
This is air naught, this is the index of refraction there. This is air, usually, I mean, it doesn't have to be air, but you'll call this N naught is just the square root of epsilon relative, and if it's air, it's just 1. That's all it is. So when we do this, we start our analysis over here. And remember, in general, when you're talking about Snell's law and you're talking about index of refraction, really, I mean, your form of Snell's law you're used to is beta 1 times the sine of theta incident is equal to beta 2 times the sine of theta transmitted. Y'all follow me on this? This is the standard way that if you have an incident angle, and this is beta 1, and then you're going to have a transmitted angle, and this is beta 2 right here, and this is beta 2. Well, here's what happens now. I mean, this is the normal. It separates these two regions. Beta is omega times the square root of mu epsilon. Do y'all realize that, class? I mean, if it's lossless, beta in general is omega times square root of mu epsilon. Well, since beta here, beta there, it's lossless, the omegas cancel, we assume it's non-magnetic, the mu's cancel, you get square root of epsilon. Square root of epsilon is the index of refraction. So I can write this equation as the index of refraction in the first region times the sine of the angle of the first region is equal to the index of refraction in the second region times the sine of the index of refraction, or sine of the angle in theta 2. And here's what happens here. Think of this as region 1, think of this as region 2. Region 2, that angle goes to 90 degrees. Do y'all follow me? There's total internal reflection. So if it goes to 90 degrees, then I can say, well, eta 1, and it would be the sine of this angle. I'll call it theta c right here. I'll tell you where this is in the book so you can see it. My drawing is not the best. This is on the top of page 410. I'm trying to keep consistent with the way he's defining the angles and everything, but if you take a look at that, you'll get it. So now, it's really, this is going to be in fiber, actually. Let me put it in terms, in his terms, so it's going to be n of the fiber, the index of refraction of the fiber, times the sine. And in Wentworth's book, this angle is theta c right there. I'm not showing you that well. So sine of theta c is equal to eta 2, or the cladding. It would be the index of refraction of the cladding. This is NF, this is N cladding here, times the sine of theta 2. Well, the sine of theta 2, sine of 90 degrees is 1. We're assuming this is the critical angle. Y'all follow me in this class? So you just leave it as 1. So I get the sine of theta critical is equal to n, the index of refraction of the cladding over the fiber. There's my first formula that I used. Now, this is the thing that's important. I'll blow that up a little so you see it. This was theta c. This was theta b, consistent with Wentworth. Follow me on this? I just expanded. Now the sine of that angle, the sine of theta, the sine of that angle is the cosine of this angle. Do y'all follow me? Follow me on that, class? So I can replace this, and I can, instead of sine of theta c, I can say that's the cosine of theta b is equal to NC over NF. Does everybody follow me on what I'm doing here? And you have to appreciate that I tried to blow that thing up. The sine of this angle, sine is what? Sine is opposite over hypotenuse, is the cosine of this angle, which is adjacent over hypotenuse. Y'all follow me? It's real important you have an appreciation for why this works. So then I go ahead and I take this and I'm going to square it, and I get cosine squared of theta b is equal to nc over nf squared. And then Whitworth says this, and he literally states this. He says the cosine squared of x plus sine squared of x is equal to 1. Or I can say cosine squared is 1 minus sine squared. So therefore, this becomes 1 minus the sine squared of theta b is equal to nc over nf squared. I bet you some of you are seeing where I'm going with this. I'm going to solve for theta b, sine of theta b. Do y'all follow me? So after that point, I rearrange terms, take this on this side, this on that side, and solve for sine of theta b, and I get this. The sine of theta b is equal to the square root of 1 minus, and then it's going to be nc over nf squared. Just for a second, I'm going to make mention of something. You see how you have nc over nf? If that isn't less than 1, that's going to be a square root of a negative term. Y'all follow me? Square root of a negative term is j. It makes no sense. You can't have it. The only way you're going to get propagation is if nc is less than nf. The fiber core has the higher dielectric. Everybody with me on this class? So now, once I have that, then I come back over here. And now I say eta naught, that's the index of refraction of whatever's over here. It's where the optical light's being fed. Typically it's air, so it's usually 1, times the sine of, and this would be theta A, would be equal to index of refraction of fiber times the sine of theta B. Well, the sine of theta B is this. Alright? So I take that and I replace the sine of theta B over here with that. So now I have NF, and then it's going to be times the square root of 1 minus NC over NF squared. Y'all with me on this? And now I'm just going to multiply through with NF, and I get the square root of NF squared minus NC squared. And if you want to, you can divide that by N0, which is usually 1 if it's there, and almost always it is. This is called the sine of theta A. Now we could solve for A by taking the inverse sine of the square root of NF squared minus NC squared over N naught. Y'all follow me? You can, if you want that angle, you can solve it. But the really important thing, this is called the numerical aperture, or NA. Now, here's why it's important. Because these fiber optic devices, fiber optic tubing in general, it's 50 to 120 microns. All right, that's super small. Do y'all follow me on this? Now, when you have light, think of a laser over here. You have to make sure that that light's coming in at an angle equal to or less than that. Do y'all follow me? And it's real easy to mess that up. It's an alignment problem. If you have something that's pencil thin and you've got a fiber optic source, you're butting it up next to it, if there's any kind of mismatch, that angle can go to heck. Your thing can move down here, so the actual, they'll use a light emitting diode to actually feed these things. Now that you exceed that angle, nothing goes in. It doesn't propagate. Y'all follow me? So the numerical aperture, the way I like to think of it, it's really a measure of the goodness of the fiber. All right, the smaller that is, the harder it is to work, which tells you intuitively that you would like NF to be as much different than NC. It would be nice if NF was like sort of twice NC. Y'all follow me? Then you'll get a big angle. That ain't the way it works though. With fiber optic materials, they're made of a core of glass, and they add dopant, and there's not a lot that they can do with this. There is very small differences in NF and NC. So that angle is inherently small. And that's the real thing about fiber optics. is this numerical aperture. That's so important, to have it large enough. So, I mean, you could say, just check this out for something typical, if we can do this problem in 1 second, to give you really a feel for this. So, Dr. Whitmer's book has a lot of stuff about different types of materials, and here he's got a fiber core of, the fiber itself is 1.465, and the cladding is 1.45. We're going to just, I want to just do this to give you an idea of how little difference there is. So if we have the fiber core, I think 1.4, I'm looking at page 411 for this one, is 1.465. And the cladding itself is 1.45, I believe, according to his example. Yeah. So if you take a look at this, I'm just going to show you how small that angle is. So if we take a look at this, we get the sine of theta A is equal to the square root of 1.465 squared minus 1.45 squared. By the way, this is probably a very realistic thing. We'll assume we're in air, so dividing by n naught won't change anything. Now, what's this angle going to be in degrees? Well, it's going to be inverse sine of the square root of 1.465 squared minus 1.45 squared. I'm sure Dr. Whitmer's book has this, but tell me what that is. Anyway, you're going to find it's pretty small.
12.1 degrees.
Anybody confirm that? It probably is. I don't know if he has. Yeah, he does. 12.1 degrees. All right, that seems like, you know, that seems like a lot of wiggle room. But when you're talking about things that are microns, like 50 microns across, and you've got a source here. Now remember that light from that source has to be, it's going to be close to it. If there's any misalignment at all, nothing works. I mean, when I say misalignment, you don't have an appreciation for this until you try to do this, but this is something, micron kind of stuff, adjusting things at the 50 micron level. Frankly, I'm not even sure how they do it anymore. It used to be something where they'd have mechanical things, you'd go in there, like doctors use this, they'd have their, basically fiber optics that feed their a lens, they magnify, and then they move these super small little things, like when they do surgery in the eye and stuff like this. My friend's an ophthalmologist and showed me some of this stuff. It's not easy to do this. That's what I'm getting at. So just remember that. Now, probably nowadays they have some workarounds, but that's the reason numerical aperture is so important. A few other things I'm going to mention. For the single mode, one of the things you want is, again, for fiber optics, when we're talking about circular fiber optics, you want only one mode, right? Now, remember, and I'm going to erase this and show it up here. When you talk about one mode, and this is step index fiber, graded index, it means there's a discrete change from here to here, and it's assumed constant, then it goes from here to here, it's constant above it. But this is where it gets interesting. And I'm gonna put it both up here. So when we talk about a slab waveguide, to get one mode only, you have the equation A over lambda naught has to be less than 1/2 over the square root of n1 squared minus n2 squared. This is like fiber cladding. Think of it that way. That's for a slab waveguide. That's a planar waveguide. where you basically have N1 and then you're surrounded by N2. And the thing's bouncing down there. Now, when you have fiber, then, and in his book, this is a different one. I don't even know what page this is on, but he has it for one mode, and I'm gonna write his equation for a single mode. One mode here, only one mode in the fiber. It's going to be lambda naught, that's free space lambda, has to be greater than 2a, or 2 pi a, pardon, 2 pi a square root of n fiber squared minus n cladding squared all over K01, and K01 comes from a Bessel function, and it's equal to 2.405. Now, I'm going to explain something about this. If you meet this condition, you have only one mode propagating. That's what you want. It's telling you how to figure out what frequencies you can propagate. And basically, with most of this stuff, because we're talking about optical fiber, they talk about light in terms of a wavelength, not in terms of a frequency. Y'all follow me on this class? It'll be a wavelength of some laser light source. Now, here's what this really is. K01 is the actual first zero of a Bessel function of the first kind, and it's actually J0, which doesn't mean a lot to you, but let me just explain this. When you take a look at a Bessel function, and I'm just going to put this versus x, this is J0 of x. When you take a look at this, a Bessel function will come down here. The first time it hits 0 is when x is equal to 2.405. It's the first zero. As you get along in your classes and into your senior coursework, and some of you go to grad school, you'll see Bessel functions. That's what it means when it says a zero, first zero of a Bessel function. And that's all it means. Now, why does this work? Because when you solve the del squared equation in cylindrical coordinates, you get Bessel functions instead of sines and cosines. Then, what you always look for is, remember how when we were doing a rectangular waveguide, we had to find the value of beta x times a that would cause the sign of that to be 0, right? Y'all remember that? And the way we found it is we found the zeros. Y'all remember? Same thing here. Even, I'm not going to go through it, but that's where that K0 comes from. That's where it's from, and you don't have to worry about it. Just understand, this is the equation. Now, I would provide you with that equation, and I'd provide you with that equation. Y'all hear me on this one? Don't go around just memorizing it. But you have to have an understanding of the application, what they mean. If you want only one mode, you've got to have a wavelength longer than this or that limitation. Y'all follow? And that's really it in a nutshell. So, the last thing we cover in fiber optics, I wish we went through the del squared equation, the field equations for this. They are a little messy. I probably could with a PowerPoint, but Dr. Whitmer's book doesn't have it. Now we want to estimate the number of modes that would be present if we're not at the single mode limitation. So when we estimate the number, and this is an estimate, estimate the number of modes, and it's approximately equal to, and the way he does it, there's a couple of ways. This is probably as good as any. It's 2 over, and he has it over pi a over lambda naught squared, and then it's going to be times nf squared minus nc squared. That's the number of modes that actually are going to be present. An estimate of it. Now, I'll tell you this much. I've never had to use that to estimate the number of modes, because single mode fiber is the only thing that really is of interest to me and stuff like this, and all the stuff I've done. There must be some reason that this is important to estimate the number of modes, and it probably has to do with cheap fiber optic systems where they don't mind multi-modes because they can actually just send out pulses of light, little packets of light that have a duration that's short, and the actual length of cabling is short enough so that they don't get too much dispersion. So what they normally do is send a pulse. It's got it's a defined width. If you freeze time for a second and just look spatially, you'd see a whole bunch of photons from here to here and then none anywhere else. As that packet travels down, there's dispersion. The more modes, the more dispersion. Or all of a sudden the photons are over a larger and larger, you might say region, spatial region, if you freeze time. Well, pretty soon the first packet will broaden enough to be into the second packet, and you can't tell where the first packet was and the second packet started. And that's when you lose any kind of fidelity. You can't tell. Yeah.
So you can't run multi-mode fiber with long distances?
Well, you could, but you garble everything, because when you're dealing with this kind of stuff, there's all sorts of simulations in this we could do. But the real thing you're trying to do, when you send pulses, even if it's single mode, they'll be spreading. There's dispersion. When you send a packet of photons, as it moves down, fiber optic disperses. But with multi-mode, it disperses really fast. And all of a sudden, if you send your first packet here, if you froze time, second packet's here. Well, as they're broadening, there comes a point where they overlap, and your photodetector can't tell one from the other. It's just a continual string, so it has nothing. Because what happens when you send these packets down, you use a light-emitting diode to create them. Then use an optical detector to detect them. And like when it's on, it's a 1. When it's off, it's a 0. Well, if it's always on, what do you do? You get nothing. That's what happens. And one thing about fiber optic cabling, and I have to say, it's different than waveguides. You're sending down packets, or slab wave, packets of light, packets of photons. And so when that stuff moves down, there's always going to be that dispersion problem that you have. You can't get around it. And what they do is they send it, usually like a single mode fiber, they're going to send packets down, and before the broadening causes any kind of a possible overlap, then there's another detector, and it takes that and takes it from the zeros to the 1, 0 to 1, and then it resends it. Then it's a nice, tight packet, and it resends the stuff down the fiber. Now, I got to tell you one other thing about this, because I don't know, there's two virtues of fiber optic that they don't talk about. One is that with fiber optic stuff, that you actually cannot, this is what was thought, you cannot go ahead and eavesdrop. You can't do any type of like wiretapping. That was the thoughts. It turned out not to be true. Pretty much you can't. It's immune to lightning can strike and everything like that. The signal will still have fidelity. But when you get real close to this stuff, they can actually take something and make it adjacent to it, and it will detect. Remember I talked about that evanescent field on the outside there? It'll detect that evanescent field, and it can figure out what's being sent. So, in fact, you can eavesdrop if somebody's using fiber optic transmissions, but it's not easy. You've got to be right up close to it. That's really fiber optic in a nutshell. Am I over? I'm not over. Yeah.
Is that how they use sensors to detect where the fiber optic line is underground when you're trying to find it to mark its go?
Usually, anything they're detecting underground, usually what they have is ground penetrating radar. And they'll look. Has anybody seen ground penetrating radar? They'll look, and it depends on the kind you have, but it's real clear when you have discontinuities from piping or anything like that, and they can figure out where it is. But I don't know what you're talking about exactly, but that's what they usually use for any kind of power lines or sewer lines or anything like that, or fiber lines. Anyway, so that's sort of what I have for you about fiber optics. Now, we're going to get a quiz on Friday. So the quiz that I'm going to give you will have to do with waveguides, not fiber. You all hear me on that? Rectangular waveguides, not fiber. The reason is the fiber stuff, frankly, it's not much of a challenge. You're going to have the equations. On the test, you'll get something about fiber optic. But for the quiz, it's just gonna be on a standard rectangular waveguide. All right, and we've done a problem in its entirety. I hope you did that. Okay, next. So, we're done with, chapter 7. And now, we're gonna start, we've got about 8 minutes left here. We're gonna be starting chapter 8, and this is with antennas. And I could bring down some antennas, but I think everybody has a pretty good idea what an antenna is. It's really just an electromagnetic transducer. It's something that can launch electromagnetic waves. And there are probably as many different types of antennas as there are people in this room that are common. There are log periodics. The typical one is just a long straight wire. It used to be called an aerial. Everybody saw this, right? It's a dipole antenna that we'll talk about. Then there are horn antennas. I brought a horn antenna in here a little bit ago, and I think everybody got to look at it. It's just a horn is nothing more than something that focuses electromagnetic energy, and that's what most antennas do. Then there are antennas that are spiral. There'll be a wire that just spirals out. Then there'll be antennas that actually have a whole bunch of prongs on them, like a log periodic, or really, there's a couple different kinds. There's Yagi antennas. There's all sorts of different shapes. But the antenna fundamentally is something that focuses electromagnetic energy when you radiate. And the same way it radiates it, it also catches electromagnetic energy. It's an exact dual, if you think about it, to what a telescope does, in a sense. All right? Basically, the only thing it does, well, think of it as, you know, these acoustic, what do you call it, acoustic microphones that are just parabolic, microphones that take all the energy, reflect it back to a central point. That's basically what an antenna can do. It just focuses stuff. Either incoming stuff is focused so you can basically get more of the signal, that you have gain from the signal from a certain point, or you can radiate and focus it where you want. So with that, now I have to talk a bit about antenna theory in a general sense. I'm going to do that, and we'll get to actually solving a lot of this stuff using Maxwell's equations in the next class. This is going to be chapter 8, and it's antenna theory, and this is some of the basics. So you're just going to have to go with me on this one. So when we have what are called a short dipole, what we mean is that the length of the antenna is much less than, or is actually less than lambda over 10. So what do I mean by a dipole? It's a good question to answer. Here, the length of my antenna is L, and I'm feeding this with some kind of a source generator like this. So if L, this is a straight wire, this is nothing more than a straight wire. You follow me on this, class? With a straight wire antenna, it's like that, where L is much less than lambda over 10. A couple of things happen. First thing is the current distribution on this. If we graph the magnitude of current on this versus position, it would be just a constant value. The wavelength's so long that there won't be any kind of standing wave set up. Y'all follow me? So current, basically the current's going to go in this direction, and then it'll change and stuff, but the magnitude of current will be the same all along that antenna. You follow me? Now what that results in, I'm not going to prove the whole thing now, I'll do that on Friday, is that you get a field, and let me do it over here because that's a little busy. This is my line of length out, and it has a current on it of I as such. Then you're going to get, call this the z-axis, call this theta. You're going to get something that's the electric field from that antenna. I can't prove this right now, so I'm running out of time, but you're going to get the electric field here that will be equal to J times eta times beta times I times the length, and this I here will be just the magnitude. We can call it I naught. Then it's going to be over 4 pi r, so it's inversely proportional to radial distance. it's going to take times the sine of theta as such, times e to the minus j beta r, and it would be in the a theta direction. Something I failed to mention, this is called the far field. And I'll explain this now. Some of this stuff's it'll all come together on Friday, a lot of this, but I just have to get this out there. So this is for a short dipole, that's the field pattern. And what do I mean by far field? Anybody want to take a guess? There's, quote, near fields and far fields. Far field is really where we're going to be at a position, and I'll tell you where the far field distance is. And this is a bit disjoint. The far field distance, D, it's actually the range R, they call it R, is greater than really lambda over 2 pi. And this is for straight wire antennas. It's not true for aperture antennas. So when I'm further than that away, I'm in the far field. So what is the far field? Basically, if you're real close to an antenna, doesn't matter the type, you're going to have capacitive energies. You're going to have an electrostatic field around it that will decay back when you actually shut the thing off. All right, that's an electrostatic energy that collapses back. You can get it just like a capacitor. You're going to have magnetostatic energy too that would collapse back. That's near field energies. Do y'all follow me? Now, when all of a sudden you're at a distance greater than this, most of the electric field is far field. It's going to be launched. It's gone. It's not coming back. Y'all follow me? So that's far field energies. And when you're in the far field, that would be the electric field. It would be in this direction, and that's how it varies. Now, in magnitude, I got one other point about this, because I'm not going to have enough time to do everything I want. So when I look at this, it varies as the sine. So how much electric field radiates straight up? Well, what's the angle straight up? 0. What's the sine of 0? 0. Nothing goes straight up. How about straight down? 0 as well, right? Where's the maximum value? Right, it's called broadside. It radiates maximum there. Now, if you were to actually get the power density, how would I get the power density if this is a radiated field, anybody? 1/2 magnitude of that E field squared over 8 and 9. Y'all hear me? If I do that, you can see it's proportional to the sine squared, can't you? Y'all follow me? Just square that. Here's what it would actually look like. If I plotted that, this would be the power pattern, that's what it would look like. It'd be a sine squared pattern. Maximum value there. We'll get into this, but then when we find where the half power points are, when the maximum value of the power at a given range goes down by 1/2, this is called the beam width. You probably heard beam width before. On Friday, we'll pick it up there. I wanted to just introduce you to some of the concepts. I'm starting with the simplest thing. And we'll do Maxwell's equations and develop this on Friday. Then we'll talk about beam width, gain, all sorts of things. Remember, quiz is on waveguides.